All right, I think we're good. So 2.4, it's all about real zeros of polynomials, and like I said, we're going to start with dividing. All right, so long division, we'll start with that. So let's say I've got 3x to the third plus 5x squared plus 8x plus 7. And I want to divide from that 3x plus 2. Okay, so I've got a polynomial in standard form. I want to divide another one in standard form. Okay, so to do that, we're going to set up a problem that looks just like a long division problem from when you were in like elementary school. So I'm going to have you practice with that real fast here. So let's say we've got 1,463 and we want to divide 12 into that. So we're going to refresh ourselves on this division. So over here we're going to do the elementary school long division. And then on the other side, we'll start working on the polynomial long division and kind of compare and contrast a little bit as we go. So let's see what you guys remember. So how do I start this problem then? I want to see how many times 12 goes into 1,463. Yes, sir?
See how many times it's going like 14.
Okay, so start with the first part of it. So technically, I mean, your brain has already skipped over this, but technically the first thing you would do is, how many times does 12 go into 1? Oh, can't do that. So how many times does 12 go into 14, right? So you're kind of going one digit at a time over. So how many times does 12 go into 14? One time. What do I do with that 1? Goes on the top. Good. All right. And then what's the next step after I have that 1 up there? Right. So we do this multiplication. 1 times 12 gets me 12, and then we do a subtraction of those numbers. 14 minus 12 is 2. Yep. Okay, then what? Oh, yeah, go ahead.
Bring down the next number.
And in fact, we can technically bring down both of them. I'll do that just to be safe here. But yeah, I really only need the next digit. And then we go through that same process. How many times does 12 go into 2? Can't do that. Okay, how many times does 12 go into 26? 2 times. So 2 times 12, 24. Subtract those. I've got 2. Bring down the 3. How many times does 12 go into 23? 1 time. 1 times 12 is 12. 23 minus 12 is 11. So then we have a remainder of 11. Or you might have seen this written as the answer is 121 and 11 twelfths. Yeah. Okay. We'll do the long division with the polynomials kind of like this, where we'll turn it into a fraction at the end. Okay, so keep that process in the back of your mind here, because we're going to do kind of that same thing. So we're going to take 3x to the third plus 5x squared plus 8x plus 7. And we're going to divide 3x plus 2 into that. Okay, so process starts out the same. You ask yourself, how many times does 3x, and you start with the first term, just like you started with the first digit over here. How many times does 3x go into 3x to the third? Or, what might be a better question in this sense is, what do I multiply 3x by to get 3x to the third? Yeah. X squared. Okay. So I'm going to put an x squared on the top. However, since it's x squared, I'm going to put it in line with the x squared. Okay. What we're going to have here is we're going to have these like columns. And so anything that's x squared is going to be lined up with the x squared. Anything that's just x is going to be lined up with the x. Anything that's the constant is going to be in the end. So we can kind of keep some order that way to what we're doing here. Okay. But same thing like we did here to get the 1, though. We got this x squared. Now, what did we do with the 1 after we had it? Multiplied it through by the 12, right? So we're going to do the same thing here. We're going to multiply the x squared through by this entire 3x plus 2. So it's going to be a little distributive property going around the bend here. So x squared times 3x to the third, x squared times 2 plus 2x squared. So that was doing that multiplication step around the side of it. Okay, think back to this one. What's the next thing we did? Subtracted. That's what I'm going to do here too. I'm going to subtract it. So this entire thing, I always put it in parentheses just so I don't forget to distribute. That whole thing gets subtracted. So down each column, subtract, subtract. 3x to the third minus 3x to the third. Gone, 0. 5x squared minus 2x squared. 3x squared. Okay, so that's the answer to my subtraction. What was the next thing that we did in the other one? Drop stuff down. Okay, I still got this 8x and this 7. So I'm going to drop each of those down. So now I've got plus 8x plus 7. And then repeat. Do the process again. What do I need to multiply 3x by to get 3x squared? Just x, right? So plus x on top then. Okay, multiply it through. 3x squared plus 2x. And then we're back to that subtraction step again, right? So take this, subtract it. These cancel. 8x minus 2x, 6x. Bring down that 7. And we got one more go at it here now. So what do I need to multiply 3x by to get 6x? 2. Plus 2. And multiply the 2 through all of it. 2 times 3x is 6x. 2 times 2 is 4. Subtract that away. 6x is canceled. 7 minus 4 is 3. So notice every time I go through this process, the first term is gone. First term is gone. First term is gone, right? That's the whole point. We're trying to get rid of that first term each time to whittle this thing down to whatever the remainder is. In this case, the remainder is 3. Okay? So like in the other one, where we had a fraction, 11/12, we got that fraction by taking this number down here, 11, and dividing it by this, right? Because that was the part whole that was left. Well, here's our part. Here's our whole. So that's going to be the fraction. So our answer to this one will be x squared plus x plus 2 plus, oops, that should be 3x. 3 out of 3x plus 2. Looks like that. And we've used polynomial long division to get to that point. Okay, so I want you guys to do a couple of these long divisions on your own. I'll give you some time to practice them here. And then I'm going to show you how synthetic division works with this. Do you guys remember synthetic division from Algebra 2? Yeah, you get rid of all the variables and you just put the numbers in and go real fast. Yeah, so we're going to refresh that in a little bit. But I want you some practice. I want you to have some practice with the long division before we get to that point. So here are the two I'd like you to work on. Okay, so we'll get that one. Well, let's make this a 2. All right, and there's your second one. All right, so I'm going to leave those up there for a few minutes. I'm going to pause my recording and let you guys practice a little bit. Okay, so I'm copying our last one that we did together here. So we had that whole polynomial, and we were going to divide that by x plus 1. Okay. So what we just talked about was, if you're dividing by something that is a binomial, then we can take what we have in this polynomial division and use synthetic division instead. Okay. And the way that it works, so we have this, it looks like a backwards L, but it's kind of like a little box. And in that box is going to go what we had in this part of our division, so our divisor. But instead of x plus 1, what goes in that box is the number that makes this 0. So what number, when you plug it into x plus 1, makes it 0? Negative 1. Okay. So in that little box, we're going to put negative 1. And then next to it is going to be what we're dividing out of, okay, which is this big long polynomial. But instead of having all the x's, really all I need are the coefficients. Because if you remember all the work that you guys were doing in that long division, really it was just the coefficients we were working with. As long as we kept them in order, in the right places, so that they all lined up right, then it would still work. So I'm going to take all of those off of there. So 4, negative 2, 1, negative 1, and 5. And we just write them straight across. And just make sure they're nice and spaced out. And then you're going to skip a line and then draw a line. Okay. So here's how it works. First number, whatever it is, just drop it down. And then we're going to do that multiplying around step. So negative 1 times 4, negative 4. Okay. And then straight down there, because I switched the sign on this to negative 1 instead of subtraction, now we just add them. So negative 2 plus negative 4, negative 6. Negative 1 times negative 6, 6. 1 plus 6, 7. Negative 1 times 7, negative 7. Negative 1 plus negative 7, negative 8. Negative 1 times negative 8 is 8. 5 plus 8, 13. So take a look at those numbers. 4, negative 6, 7, negative 8, 13. And look at the answer to that last problem that we did. What do you notice? Yeah, I know. Trying to make it exciting again. Those numbers are the coefficients of your answer of the last one you did. And not only that, this 13 at the end, that's your remainder. And so usually we put a little bar down like this to kind of separate them. But yes, here's your answer. Here's your remainder. Now, when you're writing your answer, you got to put all the x's back on them. So how do we know what x, where's the x squared, where's the x to the third? How do we know which is which?
Start with the highest one, subtract degrees.
We knew it was an x to the fourth to begin with. That had 1, 2, 3, 4, 5 terms. Now we're down to 1, 2, 3, 4. So that should be an x to the third polynomial, a degree 3. So we have 4x to the third minus 6x squared plus 7x minus 8 plus 13 out of x plus 1. Same answer. Much quicker. Okay? That's synthetic division in a nutshell. Now, the only thing that I think you guys are probably going to struggle with this is, again, remembering placeholders. If there's a missing term somewhere in the middle of a polynomial, like there's no x squared term, there's no x to the third term, whatever, then you're going to have to put those zeros in there when you do this too. Okay, otherwise you're not lining things up correctly and it's not going to all match up the way it's supposed to. So just be careful you're not forgetting your zeros when you do that. But it works. Okay, so how are we going to use this stuff with all of our finding zeros? Well, we're going to do a little bit of it here today before we're done. And the first thing I wanted to talk about was the factor theorem. All right, factor theorem says f of x has a factor x minus k if and only if f of k equals 0. Okay, so that's the definition, but I'm going to put in here which means if divided, it has a remainder of 0. And this is something we're gonna go back to this well a lot, because a lot of what we're going to be looking at is checking to see, do we have zeros or not? I got this thing, I think it's a 0. I got this thing, I think it's a factor. And I want to try and work my way through it and use some synthetic division again and again and again to check a bunch of them. Okay? So there's this key connection here that if you have a factor, you have a 0. Okay? So kind of the big idea here is if x minus k is a factor, then k is a 0. Now there are other words that we use for 0 like solution, x-intercept, all that stuff. Okay, we're going to call them zeros for now. But if x minus k is a factor, then k is a 0. Okay, so let's use that idea and see if we can figure out how we can use synthetic division to answer the following question. Let's see. So is x minus 3 a factor of 2x to the third minus 3x squared minus 5x minus 12? So what am I ultimately going to do to check that then? Divide them and then look for what? Look for 0. Look to see if the remainder is 0. If the remainder to the division is 0, it's a factor. Because think about it. What does a 0 remainder mean in a division problem? It means that the number goes in evenly, right? If something is a factor, isn't that exactly the same thing? A factor is something that goes in evenly into a polynomial. We're talking polynomials instead of numbers, but it's the same idea. It goes in evenly. Okay? So let's do the division, see what we get. So if it's x minus 3, that means 3 is going to go in the box. Then I'm going to take my coefficients here, 2, negative 3, negative 5, negative 12. And let's do that synthetic division. So bring down the 2. 3 times 2 is 6. Add those up, it's 3. 3 times 3 is 9. Add those up, it's 4. 3 times 4 is 12. Negative 12 and 12 is 0. So, do we have a factor? Yes, indeed. Yep. So we know x minus 3 is a factor. So we actually know a 0 to the function as well. What number has to be a 0 to this function? 3. Mm-hmm. Just like when you guys had quadratics and you would factor it and then take your two factors, set them equal to 0, and so solving each one of those would give you the zeros. Well, I didn't actually factor this thing, but I did find out that this particular x minus 3 was a factor, which then allowed me to know that x equals 3 was a 0 that goes with it as well. Okay? So I talked about before, there's going to be some problems where you can't factor. However, you can do some synthetic division to check, to try out a bunch of them, and as soon as you get a remainder of 0, then you have one you can use. Yeah? You could also do that. Yeah. If you think that's easier, I don't know, maybe. In this case, let's say you didn't have a calculator to use. Might not be at that point. I don't know. I mean, 2 times 3 to the third minus 3 times 3 squared minus 5 times 3 minus 12. I don't know. Some people can do that in their head pretty quick, but yeah. Okay, then yeah, absolutely. And that's an important point, though. I mean, there is that connection, too. F of 3, you know, this is what the factor theorem was saying, too, is that if you plug the number in, it should come out to 0. And so, yeah, if you feel like that's an easier process for you, 3 to the third is 27. 2 times 27 is 54. That's 18. 3 squared is 9. Oh, 27. Yep. Minus 15 minus 12. So 54 minus 27 is 27. So, yep, so that's 0. Yeah. Okay, so, I don't know. Both are pretty simple. I think if you end up with polynomials that have a degree much larger than 3, though, you're probably going to want to go with the synthetic division instead, because then you got to try and, like, you know, raise things to the 4th and 5th powers, and it gets a little messy. But yeah, that one's all right. All right, so that is the factor theorem. There's also what's called the remainder theorem, which is related to the factor theorem. And so this is kind of like the general case for everything, not just checking for factors, but so let's make sure I'm saying this the right way. So if f of x is divided by x minus k, then f of k is the remainder. Now, do you see how the factor theorem is actually just kind of a specific case of the remainder theorem? It's really doing the same thing, right? It's using the remainder theorem where the remainder happens to be what? 0. Okay? But it's saying the same thing. If you plug the number into the function, whatever you get out at the end should be your remainder. Oh, and look, if it's a factor, that should be 0. Okay. So it kind of works the same way. So if the use of the remainder theorem, I suppose, is if you're really wanting to just know, does it have a remainder or not? Or if it does, what is the remainder? And if it's easier to just plug the number in, you can do that. Okay? I'm not going to do much more with that, but that's the idea. The factor theorem exists because this remainder theorem does. Okay? So it's kind of your bases a little bit more with that remainder theorem. So we'll do one more example with this factor theorem stuff, and then we'll be done for today. I'll give you guys a little time to hang out because I don't want to let everybody else get too far behind. And plus, we're going to start something that's going to take a little bit of work tomorrow, the rational zeros theorem. We're going to want to spend some time talking about that together. All right, so let's take a look at a function. Let's do, how about 3x to the third plus 4x squared minus 5x minus 2. And I'm going to give you some numbers to test, and you're going to see which of these are zeros. Bless you. Okay. So using the skills you have at this point, and what you know about the factor theorem, what you know about synthetic division and all of that, I want you to test and see which of those 4 are actually zeros of the function. All right, 2 of them should work and 2 of them should not. So take some time, try that out, and that's where we will stop for today. Okay, and now we are officially recording too. Okay, good. All right, so we've got x to the 4th minus 9x to the 3rd plus 3x squared plus 11x minus 6. And our goal for this is to find the rational roots. Okay, so let's talk a minute about what the word rational means. What's a rational number? What does that refer to? All right, good. So any number that can be expressed as a fraction. Okay, so we're going to find all the roots of this equation, or of this polynomial, that can be expressed as a fraction. Okay. All right, and so like I said, you've done this before in Algebra 2. You guys did do a bit of this. So we'll see if this looks familiar to you. You're going to do factors of the last term divided by factors of the leading term. And when I talk factors on this, I mean like the coefficient, not the x, just the number itself. And by doing that, we're going to make a list of a whole bunch of numbers. And those are all going to be our potential rational roots. Okay, and then from that list, we're going to start testing each one systematically to figure out which ones work and which ones don't. kind of like we did at the end of class yesterday where we did synthetic division and we tested each one using synthetic division to see which ones worked and which ones didn't. Okay? So, for this particular problem then, let's start with this. What are all the factors of that last term, negative 6? Go. Yeah, they have to be integers, yep. Okay. So, and I can use positive or negative of any of these numbers, right? So you said 1 and 6. So plus or minus 1, plus or minus 6. What are some other factors we can use? 2 and 3. Okay. So plus or minus 2, plus or minus 3. Okay, those are all the different factors we could have from negative 6 that are integers. And then also I need to do factors of the leading term, and the leading term coefficient is just 1. And this list is going to be a lot shorter. What are my factors of 1? Just plus or minus 1. And so then what we need to do is do a combination of all of these, all the combinations of these numbers divided by these two numbers. Now, on the outset, that looks like it's going to be a whole ton, right? Because you've got 1, 2, 3, 4, 5, 6, 7, 8 numbers here divided by 2 numbers there. Every combination of that would be 8 times 2, that would be 16 different numbers. Now, the nice thing is when you divide some of these, you end up getting the same thing using different combinations. Okay? If you divide a positive by a positive, what do you get? Positive. If you divide a negative by a negative, what do you get? Positive. So you're getting the same thing those two ways, right? So if we look at just like taking the plus or minus 1 and dividing it by plus or minus 1, there's really only two options there, right? Could be what or what? Positive or negative 1, right? If I take plus or minus 6 and divide it by plus or minus 1, there's really only two combinations there too, right? Plus or minus 6, okay? So normally, you would have more than just one thing here for the factors of the leading term. So maybe it would be like a plus or minus 1 and then a plus or minus 2 and some other stuff. So you're still just matching them up, but the plus and minus stuff kind of like cancels itself out a little bit. So really, by dividing these things, we're just going to test plus or minus 1, plus or minus 6, plus or minus 2, and plus or minus 3. So we got to do 8 synthetic divisions then. Okay. Now, some of you guys are like, oh, geez, 8 of them, really? Yeah, we still got to do 8, but 8's a lot better than infinity. Because at least doing this, we're able to whittle it down to 8 possibilities rather than, I don't know, a whole bunch. You need one more?
Yeah, there should be one left.
Right?
That should be it then.
Okay.
Thanks.
All right, yep, no problem. Okay, so for this one, what I'll do is let's break up the class a little bit and have you guys, like, maybe every 2 people takes a different one. So you guys right here will do positive 1, negative 1, positive 6, negative 6, positive 2, negative 2, positive 3, negative 3. Okay? So what you guys are going to do is you're going to use a synthetic division. So take the number that I just told you when I pointed to you, put it in the little box for synthetic division, and see if it's going to be a factor or not, or if it's going to be a root or not, I guess technically is what we're doing. Okay. And then I'll work them all out really quickly here. Yeah, there's some of these you get about 3 steps into it, and it's like, yeah, it's not going to work. Like I was just working on the positive and negative 6, and yeah. Alright, sounds like you guys are all done, so I'm just going to finish the last one I was doing here. Answer that one. Negative 11, 22, 25, negative 50, negative 39. 2 times 39 is 78. So that's getting 72. Okay. So let's just go around the room and see if it worked or not. So positive 1, did that work? So positive 1 is a root. Negative 1, that did not work. Okay. Positive 6.
Just slightly vary off.
Yeah, slightly very, yep, a big remainder. Okay, negative 6. A lot of no on that one too. Yep. Positive 2. Did not work. No. Negative 2. No. Positive 3. No. Negative 3. No. Okay. So the only rational root we have for this one, and I'll show you. I did synthetic divisions here for like the first 6 of them, and then got tired of it. So yeah, the only one that came out to have a remainder of 0 was this first one. Okay. So the only rational root for this particular function is x equals 1. Okay. Now I could have gone through, and done the rest of these synthetic divisions. If I was doing this problem by myself, I'd have to do all of them, but x equals 1. That's it. And sometimes it might seem kind of frustrating to you, but at least you're arriving at an answer. Sometimes none of them work. You don't have any. So the particular function cannot be factored at all. There are no rational roots whatsoever, and that's your answer. Okay? Now, this being said, does that mean that there are no other roots whatsoever for this particular function? There's just no more rational roots. Right. So we don't know about the other ones necessarily with this one because we can't really go any further with this. We can take out the 1 and see what's left over, but then we're kind of stuck. So I'll do one more of these with you guys. It's not going to be quite as large this time around. But on this one, we're going to take a look at a couple of roots, and we're going to see if we can take out all the rational roots and then use that to find more that are not necessarily rational roots. Okay? So let me quick get this all together here. Well, try a different one here. So, sorry, I got to quick multiply stuff together here to get the new one. Okay. So, and I'm sorry, these take a lot of space on the page too. So how about x to the third plus 2... Nope, I lied. Plus 4x squared. Minus 3x minus 12. Okay, so it's going to be factors of 12 divided by factors of 1. Okay. So what that's going to get us as far as numbers we need to test, I'll just list them off for you here. So plus or minus 12, plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. Oh, and a 4, right. Okay, so we've got 1, 2, 3, 4, 5, 6, so 12 of them to test this time around. Okay, let's break this up again. I'm not going to write down all the synthetics this time because you guys can do that, but we'll break it up again. So 12, negative 12, Angel. 6, negative 6. 3, negative 3. 2, negative 2. 1, negative 1. 4, negative 4. Pick your favorite. All right. Give it a try. We'll see which ones work. Yeah, if you figure out it's not working, you can just stop. Just like before. I mean, you can kind of tell after a while. But okay, so are we all through our synthetic division here? Yeah. Okay. Anybody find one that actually worked? Yes. Positive 4 or negative 4? Negative 4. Anybody else? Good work, because that was the only one that was supposed to work. So nice. All right. So let's just look at that synthetic division with negative 4 here. Okay. So negative 4, then we got 1, 4, negative 3, negative 12. Okay, so we work this one out. 1, negative 4, that's 0. Negative 4 times 0 is 0. Negative 3, positive 12, yes. Okay, so if you don't have this one written down, write this one down because we need the answer to this to help us into the next step here. So once I've done this division, think about when we did synthetic division yesterday. We were able to take this answer and rewrite it as a polynomial, right? So what polynomial is that for this one? If I have 1, 0, negative 3. Yeah. Okay. So what I have now, once I've taken out that negative 4, I have x squared minus 3. So what that means is that this original polynomial should factor to that. Does that make sense? So this is equal to this. Okay? Because the negative 4 worked, that means that x plus 4 is a factor. That's the part of the factor theorem we talked about yesterday. Okay? So, and then whatever's left over should be what you multiply with that factor to get the original. Okay? So let's take a look at this thing. Because remember, ultimately what we're trying to find are zeros, right? So if this is equal to 0, I know one of the zeros because I found it with a synthetic division and it matches the factor. I know from this one, x equals negative 4 is one of my zeros. It's the only rational zero, too. We determined that. But we've got this x squared minus 3 left over as well, right? And we can still get some more zeros out of that one. So if I work through that, x squared minus 3 equals 0. That's something we can solve for this, right? So I got to add 3 to the other side, and then do what? And then square root both sides. So x equals plus or minus root 3. How many roots do we have altogether here? 3. And that should make a bit of sense, right? Because it's a cubic, right? So it should have, at most, 3 roots. And yes, it has 3. How many of those 3 roots are rational? Just the one, right? We found 1 rational root and 2 irrational roots. And remember, irrational numbers are numbers that you can't express as fractions, like square roots. Square roots are like the classic irrational numbers. Okay? So 1 rational, 2 irrational, 3 roots altogether, but we found them all. Okay? For this particular problem, I was able to go get those other ones because I had something I could solve that was left over. This one that we did over here, the first one we worked on, that was this big 4th degree thing, and the only thing we found was a 1 that worked. Okay? Take a look at the end of that synthetic division. I have 1, -8, -5, 6. Is that something I could continue to factor and work with? No, because that would be a cubic, right? It'd be x to the third minus 8x squared minus 5x plus 6. That's not something I'm able to factor. So I'm stuck. So the only thing on this one I can say is, well, I know there's a rational root of 1, but that's it. There might be some other irrational ones, but I'm not able to find them. Okay? So it all depends on what are you left with when you take the rational ones out, and then can you continue to move on to find some more? Yeah?
If you did have x squared minus 8x squared minus 5x plus 6, could you do another synthetic division?
You couldn't. Because you're saying, like, could you do another rational root test and keep going with it? You can't, because whatever is a factor of the thing you start with should also be factors of this. Okay? And you've already tested all the rest of them. So you know none of the rest of those are going to work, so you're still stuck. Yeah, you could try the rational root test again, but it's going to come out the same. Yeah. So, all right. So this is going to be kind of your task for a lot of this assignment today, is going to be using the rational root test to find the rational roots, and then looking to see, with what I have left over, can I go any further and get some more? Okay? So sometimes you can, sometimes you can't.